Today we're going to continue reading Alice in Quantumland. This is the cover of the book, right? Alice in Quantumland by Robert Gilmore. We are in chapter 8 called Castle Rutherford. All right. I want to welcome everybody as you arrive. If you're watching on the replay, thanks for watching. Thanks for reading with me. This is my channel, Ms.Carmina Reads. I'm Ms.Carmina. Support us with a like. Don't forget to subscribe. Put on your notifications. Send me gems, super chats, whatever you're able and willing to do. I appreciate all of it. I love all of you. Thank you for being here. So let's continue. Here, Alice said, finally, the door was completely open, and still she could see nothing. Were the nucleons invisible? Remember, she's inside an atom. Here I am, snapped an irritated voice from somewhere below the level of Alice's knees. Startled, she looked down, and there, standing in front of her, was a small figure. It looked not unlike the electrons she had seen before, except that somehow there was an aura of power about it, and, like her companion, it was wearing dark glasses. However, when Alice remembered how far she had shrunk on her way to Castle Rutherford, she realized that this figure must be far, far smaller than the electrons than the electrons had appeared to her before. I thought you told me the nucleons were larger than the electrons, she exclaimed, turning indignantly to the photon. She felt angry that she had been so deceived. How dare they? Why, most informed citizens agree that they are indeed larger, and I am sure you would not wish to question my word over so small a matter. Of course, the nucleons are much heavier than the electrons, and so they are inclined to be much more localized. As they are 2,000 times heavier, they naturally have 2,000 times more rest mass energy, and it is widely accepted that they are in the region of 2,000 times more localized. Even when they are having the same energy, as an electron type guy, this means they are apt to occupy less space, and so they may seem to be smaller than the electrons, but informed opinion is that they are in actual fact larger. Yes. Compared to the citizens of the nucleus, the atomic electrons are such parties as have a very little energy or momentum at all, and are by no means very localized. They form considerable electron clouds, which hang around in the vicinity of the nucleus and are very large indeed. They spread out over a volume which is hundreds of thousands of times far farther across than the nucleus. As Alice looked around, she could see, excuse me, she could see great gray clouds surrounding them, clouds which stretched away as far as the eye could see. It was a strange thing to think that these were the electrons that she had seen so often before, but now seen from the viewpoint of much more compact scale. The neutron, which had greeted them, for such it was becoming increasingly impatient with this exchange. Don't just stand there, whoever you may be, it snapped querulously, querulously, yes. Hi, good afternoon, disgusting clan. Um, and hi, Robin. I am reading Alice in Quantumland by Robert Gilmore. We are reading chapter 8 right now. Thank you for your likes. Thank you for your support. Thank you for being here and watching. Don't forget to subscribe. Um, where was I? whoever you may be. Um, don't just stand there, whoever you may be, it snaps querulously. Come closer so I can identify you. Why, he cannot see us, realized Alice. I do believe he is blind. All neutrons are in such condition, as most people admit, replied her escort. These parties are not such as have any interaction with photons, or hardly any. Having no electric charge of their own, neutrons are citizens who do not have much long range interaction, being only given to interactions of very short range indeed. Such a party is not much at recognizing others until they are close enough to touch. Excuse me. They moved up close to the neutron until he bumped into them. Ah, there you are, he exclaimed sharply. Come in and let me shut the door. It is much cozier inside. He ignored the photon, of whom he was largely unaware. Alice was interested to note that the photon simply faded into the castle's fortifications, which were, after all, composed of virtual photons emitted by the charge of the nucleus. Alice followed the neutron into the castle, which I'm so sorry. I'm so sorry, you guys. Alice followed the neutron into the castle while he felt his way down the rough stone corridor. This passage was very narrow, but seemed obligingly too wide at their approach, so that there was always just enough room to pass through. Alice found this behavior rather eerie, but she was never sufficiently sure that it was actually happening to make any comment. Now that she had met him, the Nuclean whom she was following did not seem as threatening as she had feared. Impatient, yes, but not in any way sinister. He reminded Alice of a distant uncle of hers. Together, they entered a tall, vaulted central chamber of bare stone. The walls rose sheer on every side and vanished into the shadows of the ceiling. Around the walls, overhead were arched openings, or overhead, excuse me. Overhead, o- overhead were arched openings leading to various higher levels, vaguely reminiscent of the electron energy levels that Alice had seen in the atom outside. The floor area was of moderate size and was crowded with as many particles as it could contain. But as Alice and her companion entered, she clearly observed that the massive stone walls drew back slightly to create just the right amount of extra space needed to accommodate the new occupants. You can say your story, Lunatic 90, if you want to. Alice was quite sure of what she had seen this time and commented on the movement. That is the effect of the self-consistent field within the castle, she was told. Like electrons and all other particles, we nucleons have to occupy quantum states, and the available states here are controlled by the local potential well. In the case of the electrons in the atom, that potential well is provided by us. The electron states are fixed by the electrical potential, and we control that potential. The atom is our territory, and the potential energy of the electrons within it is controlled by their distance from the positive electric charge of the protons in the central nucleus. By means of the electrical potential produced by this charge, we in the nucleus control the electron states, and the electrons must fit into them as best they can. In our own case, the situation is different. We ourselves provide the potential for our own nuclear states. If you provide the potential in both cases, surely that makes the two cases the same, protested Alice. No, it makes the two cases quite different. You see, in the atom, The potential is provided mostly by the nucleus, so that the states, although the nucleons do not themselves make use of them. The potential controls the states which give the probability distributions for the electrons, but the electrons which use them have a little effect on the potential. The atomic potential is much the same wherever the electrons may happen to be. For the nucleus, on the other hand, the potential that we are now in is produced by the collective effort of all the nucleons within it. We have a very democratic system ourselves, though we rule the electrons autocratically. Our collective potential fixes the states which are available for us, nucleons, to occupy, and so controls the probability distribution. This distribution subsequently controls the potential, as I said at the beginning. It is a vicious cycle, as you might expect for the nuclear family, and you can see that the states we inhabit will naturally change as the distribution of nucleons changes. If the nuclear potential produced by the same electric charge as the potential which holds the electrons, is the nuclear potential produced by the same electric charge as the potential which holds the electrons? Asked Alice, who thought that she should get this point clear in her mind. Oh no, quite the reverse, in fact. The electric charge in the nucleus is all carried by protons. We, you are bound to see some protons over there. He waved in the direction of the nearby particles. Alice glanced over and could see more neutrons, which looked just like her companion. Scattered among them were some other particles, which looked distinctly more assertive. Were where the neutron had been slightly irritable, these appeared to be a in a state of barely suppressed fury. The protons all carry positive charges, and particles which have the same sort of charge repel one another, you know. Protons are forever flying into a temper with each other and threatening to rush off. It is very difficult to keep them together, I can tell you. Don't the electrons have the same problem then? I should have thought that they would. If all electrons have a negative electric charge, then any two of them will have the same sort of charge and should repel one another. That is quite true. They do repel one another. However, you must realize that the electrons are relatively spread out and diffuse, and their charges are widely separated, so the repulsion they produce is fairly weak. The attractive force from the concentrated positive charge in the nucleus is able to keep them in order. The protons in the nucleus are crowded close together, so the repulsive force is very strong. The electrical forces threaten to tear the nucleus apart. See the end of chapter note 1. Let's do it, you guys. Let's see what the end of chapter note 1 says. Oh, here we are. There is only one note, so let's read it. Almost everything in the physical world may be seen as caused by the interplay between electrons and photons, virtual or otherwise. The properties of solids for individual atoms and of the chemical behavior which comes from interplay between atoms all reduce to an electrical interaction between electrons. As well as the electrons which interact with the rest of the world, there is within the atom a positively charged nucleus. The nucleus is not held together by electrical forces, quite the reverse, in fact. The atomic nucleus contains neutrons, which have no electrical charge, and protons, which are positively charged. Within the small space of the nucleus, whose radius is typically 100,000 times smaller than the overall size of an atom, the mutual repulsive force of the protons is enormous. This electrical force tends to tear the nucleus apart, so there must be an even stronger force which holds the nucleus together, one that, for some reason, is not evident elsewhere. Such a force exists, and it is called the strong nuclear interaction. Although it is strong, it has a very short range, so that its effects are not obvious outside of the nucleus. This strong interaction is produced by the exchange of virtual particles, just as the electrical interaction is produced by photon exchange. Photons have no rest mass, but the exchanged particles in the strong interaction are relatively heavy. They must get their rest mass energy through a particularly large quantum fluctuation, which is only possible for a very short time. Such heavy virtual particles are very short-lived and unable to travel far from their source, so that the interaction they produce is consequently of short range. And that's it. That's the end of the note. Where did we leave off? Oh, it's at the end of chapter note 1. Right here. Welcome, everybody. Thanks for joining. Here we are. Coffee break. In that case, what does keep you all together? Asked Alice reasonably. That is achieved by a completely different force, a strong force, in fact. The strong nuclear interaction is what it is called. The strong nuclear interaction is very powerful. It is able to overcome the disruptive electrical repulsion within the nucleus, even though it has no obvious effects outside the nucleus. It is a short-range force, you see. Inside the nuclear forces are dominant, but outside, there is little sign of them, and all that anyone sees is the electrical field due to the positive charges carried by the protons. We nucleons hold firmly onto our immediate neighbors when they are within reach, but we are not really aware of those farther away from the crowd, and have very little effect on them. Ever since she had entered the central hall of the castle, Alice had felt rather uncomfortable. Now she experienced a particularly eerie feeling, and sensed that something was now in the chamber which had not been there just before. She looked around her and could see nothing. Then she looked upwards towards the ceiling. She dimly perceived the great curved flank of some vast rounded shape which passed through the dim shadows of the soaring space above her head. It was obviously but a small part of of some much larger object which looked vague and tenuous, like a ghost, and which was drifting through the surrounding walls as if it did not exist. Alice exclaimed aloud, and then she had to describe what she was seeing to the neutron, who had not to the neutron, who had not been able to see it, of course. Ah, that will be an electron, he said. They fill the entire volume of the atom, which means they pass through the nucleus as well as elsewhere. Electrons are completely unaffected by the strong interaction, so they are not aware of us when they do pass through. The nucleus is a tiny part of the volume occupied by electrons, so they do not see very much of so they do not see very much of them. So we do not see very much of them here. Well, actually, I do not see them at all, but you know what I mean. Um Is this strong interaction not caused by photons then? Alice inquired. She had been told that photon exchange hold atoms together, but she had understood that that was due to the interaction between electric charges, and she gathered that this was something quite different. You are right. It has nothing to do with photons. It is caused by particle exchange. All interactions are, but it involves a different sort of particle. The strong interaction is in fact caused by the exchange of many different particles. the most evident of these being called pions. These are, of course, no, excuse me, these are of necessity bosons, as they are created and destroyed during the exchange process. Pions have much greater mass than photons. Indeed, photons do not have any mass at all, which makes them quite inexpensive to create. In energy terms, pions have a mass about 300 times that of an electron. They may still be created using an energy fluctuation as allowed by the Heisenberg reaction relation, but the fluctuation must be very large to provide the rest mass energy for the pion, so it cannot last for long. In the available time, the pions cannot get far from their source, so they can only be exchanged with particles which are close at hand, almost touching, in fact. The strong interaction is consequently of very short range. Consequently, of very short range. At this point, the disturbance broke out. Two of the protons had had a sudden and violent argument and were threatening to storm off in opposite directions. Neutrons rushed in to separate the contestants and keep them well apart, so diluting the strength of their mutual repulsion. While the neutrons crowded between the protons to increase their separation, they also grasped them firmly to hold them within the nucleus. You see how we neutrons are necessary to hold the nucleus together, particularly in the larger nuclei, remarked the neutron. In a nucleus, every proton repels every other proton, not just those immediately next to them, as is the case for the strong interaction. The repulsion rises rapidly with the number of protons in the nucleus, and this means that heavy nuclei, which have a large number of protons, need proportionally more neutrons to make them well away, to keep them well away from one another, so that their repulsion does not overwhelm the attractive force exerted by their immediate neighbors. The family of nucleons comes from two distinct clans, the protons and the neutrons. The lineage displayed on the wall over there shows how they combine. He indicated a large diagram hanging on the wall, among various other symbols and heraldic decorations. This showed a large and fanciful drawing of a proton and a neutron at the top of two corners of the chart. Down the center were listed the different nuclei in which the family were involved. Alice saw that they were identified by the same labels had that she had seen marking the different atoms at the Mandalay Marina. On close examination, she noted that the labels were slightly different. There was another number given for each one. Now, the nuclei were given as 1H1, 2He4, 3Li7, and so on. From the original proton and neutron at the top of the picture, lines were drawn to the various nuclei listed. There was one line from the proton to the 1H1 nucleus, and no line at all from the neutron. To the 2H4 nucleus, there were two lines from the proton and two from the neutron. Thereafter, many nuclei had apparently equal numbers of lines from the proton and from the neutron. As Alice looked towards the bottom of the chart, she saw that each nucleus depicted there had many more neutron lines than proton lines. That chart shows the different nuclei are how the different nuclei are populated from the two distinct clans of nucleons. The first number tells you the number of protons involved. This is the same number of electrons which can be controlled and hence decides the chemical behavior of the atom. The second number gives the total number of nucleons which populate the given nucleus. Lighter nuclei have the same number of protons as of neutrons. A carbon nucleus, for instance, contains 6 protons and 6 neutrons. The repulsion given by 6 protons, each repelled by every single one of the five other protons is still not enough to overcome the attraction caused by the strong interaction. Here in our uranium nucleus, on the other hand, we have 92 protons. The repulsive force between all the different pairs of protons is now very large, so a relatively large number of neutrons is needed to keep the protons apart and dilute their electrical repulsion. In our nucleus, we have all of 143 neutrons. The number of neutrons need not be quite the same in every uranium nucleus. For a given element, the number of protons is always the same, since this fixes the number of electrons and hence the chemical behavior. But the number of neutrons does not have much effect on the chemistry of the atom and can vary slightly from one nucleus to another. Nuclei of an element which have different numbers of neutrons are known as isotopes. We have 143 neutrons in this nucleus, as I said, but many uranium nuclei have 146, which makes them a little more stable. I have heard of stability before, said Alice. I thought that atoms were completely unvarying, and although they might take part in different compounds, the atoms themselves last forever. Not entirely. The walls of the nuclear potential barrier serve to keep us inside, just as the Coulomb barrier keeps other protons out. Occasionally, however, there is penetration and the nucleus is changed in some way. It works both ways. Particles outside the nucleus might break in, or some from among our complement may try to escape. The reason that protons and neutrons stay in the nucleus is the same as the reason the electrons stay in the atom. Because they require less energy, they are uh because they require less energy where they are than they would if they were outside. The decrease in energy now from the value they would have outside the nucleus is called the nuclear binding energy, or BE. There are energy levels for nucleons with the nucleus in much the same way as for electrons in the atom, and as neutrons are not identical to protons, these levels may be filled by neutrons and with protons independently. Because the level filling process is the same for neutrons and protons, stable nuclei tend to have equal numbers of the two types. For the heavier nuclei, which have larger numbers of protons, the proportion of neutrons is greater. As I have described already, for all nuclei, there is a ratio of protons to neutrons, which gives the most stable atom. An excess of either type will give a tendency to instability and some form of decay. I am forced to admit that in uranium, the repulsion between the protons is so great that the nucleus is barely stable at the best of times. Any disruption of the balance between protons and neutrons could well be disastrous. Suddenly, an alarm trumpet sounded, and a strident voice echoed through the vaulted chamber. Alert! Alert! Condition Alpha! We have an escape attempt in process! Before I continue with this escape attempt, I will read the blurb of a little bald scientist. In large nuclei, many nucleons Um, in large nuclei with many nucleons, the repulsion between all the protons becomes proportionately stronger, and the nuclei may be unstable. They may undergo radioactive decay, where the nucleus emits an particle which is a tightly bound group of two neutrons and two protons, which penetrate through the Coulomb barrier. Neutrons may also undergo beta decay, where an electron is created within the nucleus and immediately escapes because electrons are not affected by the strong interaction. Nuclei may also emit gammas, which are just high energy photons. All right, very interesting. Alice looked around to see if she could see any cause for this alarm. Everything looked much as before. There was considerable movement among the assembled nucleons, but then they, like other particles which she had encountered, were always in continual agitation. So that was nothing new. She watched carefully. She noticed that a small group of particles, two protons and two neutrons, were moving together through the crowd, holding tightly to one another. They would rush up the wall, collide with it, and bounce back, and rush across the chamber, collide with the opposite wall. Alice was strongly reminded of the person she had seen trying to penetrate his locked door when she first arrived in Quantumland. She commented on this, and her companion she commented on this to her companion, and he replied, "That is alpha particle clustering that you are describing. An alpha particle is a group of two protons and two neutrons which will bind together so tightly that they act as one particle. As it contains two protons and as it contains as it contains two protons, the alpha particle is repelled by the overall positive charge of the protons and is trying to escape, but is prevented by the wall around the nucleus. The group is trying to tunnel out. They are planning to escape the barrier penetration, and sooner or later, of course, they will succeed." "How long is it likely to take them to manage it?" asked Alice curiously. "Oh, a few thousand years, I should think." "Don't you think it's a bit premature to sound the alarm then?" inquired Alice. "It sounds to me, excuse me, it sounds to me as if you have plenty of time to deal with such an escape without having to panic." Ah, but we cannot be sure of that. It will probably take them thousands of years to escape, but they might get out at any moment. There is no way of being sure. It is all a matter of probability. "Are all escapes from the nucleus by barrier penetration then?" asked Alice. "Not at all. Alpha emissions is by barrier penetration, as I have just stated. We also get beta and gamma emissions, and neither of those requires barrier penetration." "What are they then?" asked Alice dutifully. She suspected that she was about to be told whether or not she asked, but it seemed more polite to inquire. Gamma emission is photon emission, much as you get from the electrons in the atom. When an electron has been excited to a high state and then drops back to a lower one, it will emit a photon to carry off the energy it released. The same thing happens when an excitation of the nucleus and charged rearranges the charged protons. A photon is emitted when the nucleus returns to the state of lower energy. Because of this interaction, energies in the nucleus are so much greater than in the atom generally. The gamma photons have a much higher energy than those from the atomic electrons. Indeed, they will have some 100,000 times more energy, but they are still photons. Don't forget to subscribe, y'all. Beta emission is the emission of an electron from the nucleus, her informant continued. "I thought you said that there were no electrons in the nucleus," protested Alice. "You said that the electrons were not aware of the strong interaction and just drifted through occasionally." "That is quite true. There are no electrons in the nucleus. If the nucleus cannot hold electrons, And there are no electrons in the nucleus, said Alice patiently. How can one escape from it? That does not make any sense. It cannot escape unless it is there to begin with. It is because the nucleus cannot hold electrons that they do escape from it so readily. The electrons are produced right inside the nucleus in a weak interaction, and, of course, as the nucleus cannot hold them, they immediately escape. It is quite straightforward when you think about it, said the neutron kindly. That may be, said Alice, who felt that it was not at all clear yet. But what is a weak interaction? How do the electrons? Once again, a trumpet sounded, and a herald somewhere in the top of the chamber cried out, "Attention, everyone! The castle is under attack! We are besieged by a hot plasma of charged particles." "Oh dear," cried Alice, "that sounds serious." "No, it isn't really," replied a nearby neutron soothingly. "None of the charged particles in the plasma are likely to have enough energy to breach our defenses. Come and see." He led Alice through the various galleries and energy levels within the castle until they came to a position from which Alice could view the outside. She saw other nuclear castles in the distance and spread across the plain, a number of protons moving quickly around. Those protons are from a hot hydrogen plasma. Alice's companion told her. In a plasma, the atoms have lost some of their electrons and become positive ions with an overall positive charge. The nucleus of hydrogen contains only a single proton, so when a hydrogen atom loses its electron, there is nothing left but a proton. Plasma can be made very hot, and then the protons rush out with a lot of energy, but not enough for them to break in here, he finished complacently. Alice watched some protons come running towards the nucleus, and on an on up Alice watched some protons come running towards a nucleus, and on up the curving base of its wall, and on up the curving base of its wall. As they rushed towards They moved more and more slowly as they lost their kinetic energy, eventually coming to a halt a short way up the wall. From that point they slipped back down again and rushed off in a different direction than that from which they had come. You will see, even if I can't, that they are having no success at all at actually getting inside, continued Alice's guide. Could they not get in the barrier penetration then? Asked Alice. Well, yes, they could in principle, but they spend so little time near the nucleus that it is really most unlikely. At this point, Alice noticed a disturbance in the distance. Something was quite getting closer at a most remarkable speed. "What is that approaching?" she asked rather anxiously. "I have no idea," answered the neutron. "It is something. Is there something approaching?" Alice realized that the neutron could not would naturally be unaware of the approach of the fast charged particle as it came galloping up with plumes of scarcely seen virtual photons trailing from it in its whirlwind passage. As Alice was describing its appearance to the neutron, the newcomer arrived at a castle in his path. With little apparent reduction in his mad onward rush, he ran up the barrier wall and over the top. The moment a moment later, Alice saw him galloping off into the distance, apparently little affected by his encounter. She could not say the same for the nucleus he had entered. This had burst completely asunder, and large portions of it were flying off into different directions. Alice completed her description of the event. "Ah, that would be a cosmic raider," We very occasionally get one passing by. They come from somewhere way outside our world, and they have enormous energy. To them, the energy needed to cross the Coulomb barrier of a nucleus is is as nothing, and it presents no barrier at all. We have no defense against them, but fortunately, they are, as I said, very rare. Looking down on the sea, on the area outside, Alice could make out a few unobtrusive figures moving quite slowly and steadily about. Oh, look! She cried, forgetting who her companion was. There are more neutrons moving about over there. This is a very strange illustration. See it down here? What? Cried the neutron by her side. Are you sure? This is serious. Come, we must get down the main hall at once. He rushed Alice back down through the successive energy levels to the hall she had first entered, ignoring her protests and that there had not been very many neutrons outside and that they had not had much energy at all, really. Hardly had they arrived when, without warning, an invading neutron popped right through the wall and landed in the middle of the chamber, on top of all the other particles. This was not one of the normal occupants of the nucleus, but one of the foreign neutrons which had come in from the outside. Alice remembered that the virtual proton had told her how the Coulomb barrier had no effect on neutral particles and how she herself had come in through the barrier without difficulty. In the same way, this neutron had entered uninvited. All right, guys and girls, we're going to continue reading this book probably next week since today is Friday. So I want y'all to have a great weekend, safe weekend, and I will see you next week. Love you. Thanks for joining. Remember to subscribe and like and share and everything beautiful to help this channel grow. Love to